Okay, hi again everyone. Here we are on page 17 of our Calc 3 notes, getting into section 12.5, which we're talking about lines and planes in space. So first of all, we're going to talk about a line. So I want you to consider this line I've labeled L through in space. We know one point on that line, the point P naught. X naught, Y naught, Z naught are its components. So we know, are its coordinates. So we know one point on the line. And we also know a vector v that the line is parallel to. So the vector v is parallel to this line. Vector v has components v1, v2, and v3. So any other point on that line P, which has components x, y, z, coordinates x, y, z, whatever they are, the vector from P naught to that P is a scalar multiple of this vector v, right? Because it's going to be parallel to v. So if it's parallel to v, it's either going to be exactly equal to v if it was the same length, or it'd be some scalar multiple of that vector v, because it's in the exact same direction. So in other words, the vector p naught p is t times the vector v, where t is a parameter. In other words, t is some number multiplied by v. It's a scalar multiple of v. So what is the vector p naught to p? It's x minus x naught, right? X minus x naught is the first component. Y minus y naught is the second component. Z minus z naught is the third component. And that's equal to t times the vector v, which is v1, v2, v3. So I could just do some basic algebra. If I have one vector equal to another vector, then the components are equal, right? So x minus x naught is equal to t times v, etc. But I could also break this components, these up here, to x, y, and z as this one vector, and then take out the x naught, y naught, and z naught and bring it to the other side. So in other words, the vector x, y, z is equal to the vector x naught, y naught, z naught plus the vector plus t times the vector v1, v2, v3. So this vector here, x, y, z, is actually pictured here. I drew it with dotted lines. I didn't want it to clutter up our picture. It's the vector from the origin to the point P. That's r of t. So whenever you see the vector r of t, it has these components, x, y, z, where those are the coordinates of its terminal point, x, y, z. Equals x naught, y naught, z naught, which I'm calling this vector here r naught, right? This is the vector r naught. Again, I drew dotted lines so it wasn't cluttering up my picture, plus t times v. So this is actually the vector equation for a line in space, a line in 3 dimensions. So there it is right here. A vector equation for the line L through the point P naught, which has components x naught, y naught, z naught, parallel to a vector v, is given by this equation. R of t equals r naught plus t times v. So you have to remember what r of t represents and what r naught represents, okay? R is the position vector of a point, P, which has coordinates x, y, z on the line L, and r naught is the position vector of that point P naught, right? These are position vectors. So what are the parametric equations for a line then? What you do is you just look at the components of each vector. So if I have vectors that are equal, that means that their components must be equal. So x must be equal to x naught plus t times v1, and y must be equal to y naught plus t times v2, and z must be equal to z naught plus t times v3. Putting all of those together right here gives me what's called the parametric equations for a line. Often we don't write it. We just know that t can be any scalar. But if we write minus infinity less than t less than infinity, that says t can be any number, any scalar between minus infinity and infinity. We assume that's true. Usually we don't write it unless we only want to specify a line segment, right? We don't want the entire line from minus infinity to infinity. We don't want this line as it extends to infinity in either direction. We just want a line segment. Okay, so for our first example, example 17 in this section, find parametric equations for the line through a point, right? Parentheses means a point, minus 2, 0, 4, parallel to v, the vector 2i plus 4j minus 2k. So this gives you everything you need, right? This is your x naught, y naught, z naught. These are your components of your parallel vector. So x equals x naught plus t times v1, right? But we typically don't write it as t2. We write it as 2t, so that's why you see it in that order. Y equals y naught, which is 0, so we don't write it, plus t times v2, in other words, 4t. And z equals z naught, 4, plus t times v3, but that's again written as minus 2t.